Hello everyone, once again welcome to my YouTube channel Physics with Dr. Sanjay Bhargava. In this video we are going to study about Avalanche Transit-Time Devices, Read Diode, Avalanche Multiplication in Read Diode, output power and efficiency of Read Diode. So we begin with introduction of Avalanche Transit-Time Devices. Till now we have studied something called transferred electron devices or the gun oscillator. They operate by the application of a DC voltage to a bulk semiconductor. There are no PN junctions in this device. Its frequency is a function of the load and of the natural frequency of the circuit. This is what we did in the last 6 videos. The gun oscillator, it operates by the application of a DC voltage to a bulk semiconductor. It has no PN junction in this device. The frequency is the function of load and of the natural frequency of the circuit. Now, let us see what happens in Avalanche Transit-Time Devices. The Avalanche Transit-Time Diode oscillator, they rely on the effect of voltage breakdown across a reverse biased PN junction to produce a supply of electrons and holes. So avalanche basically means some sort of multiplication, and here it represents multiplication of charge carriers. So what does the Avalanche Transit-Time Diode depend upon? किस पर depend करता है? It relies on the effect of voltage breakdown across a reverse bias junction to produce a supply of holes and electrons. The Avalanche Diode oscillator uses carrier impact ionization and drift in the high field region of a semiconductor junction to produce a negative resistance at microwave frequency. These devices are also based upon the concept of negative resistance. TDs were also based upon the concept of negative resistance. There the negative resistance was due to decrease in the drift velocity of electrons while moving in the bulk sample on increase of electric field. But here the Avalanche Diode oscillator, what does it use? Carrier impact ionization. That means collision and drift in the high field region of a semiconductor junction to produce negative resistance at microwave frequencies. Read theoretically analyzed the negative resistance properties of idealized N plus P IP plus diode and observed 2 distinct modes of avalanche oscillator. One is the impact mode, that is impact ionization, and avalanche transit time operation. In this mode, the typical DC to RF conversion efficiency is about 5 to 10% and frequencies are as high as 100 GHz with silicon diodes. The other mode is the trapette mode, that is trapped plasma avalanche triggered transit operation. Its typical conversion efficiency is from 20 to 60%. So we are going to study basic properties of the red diode and the impact mode, that is N plus P I P plus. N plus means highly doped N-type semiconductor. P-type semiconductor represented by small p, intrinsic semiconductor represented by I, and P plus means highly doped P-type semiconductor. There are 2 distinct modes of avalanche oscillator. One is called the impact mode, IMPATT, which represents impact ionization, avalanche transit time operation. In this mode, the typical DC to RF conversion efficiency is 5 to 10% and the frequencies are as high as 100 gigahertz with silicon diodes. The other mode is the TRAPATT mode, which represents trapped plasma avalanche triggered transit operation. And here the typical efficiency would be ranging from 20 to 60%. Let us physically describe red diode. The original red diode with a doping profile and DC electric distribution that exists when a large reverse bias is applied across the junction is shown in the figure on the next page. The red diode is an N plus PIP plus structure where superscript plus sign indicates very high level of doping and I or V refers to the intrinsic material. These devices consist of two regions. One is a thin P region at which avalanche multiplication takes place. This region is called as high field region or the avalanche region. Just look at the different regions here. This would be called as the avalanche region, that is this one. From here, that is this boundary to this boundary, it is basically called as the space charge region, while from here to here it would be called as the drift region, and from here to here it would be called as the inactive region, right? So what is the nature of the field distribution? Here the field first here increases, becomes maximum at this point, then decreases, and in the drift region remains constant and decreases at this boundary. Similarly, let us look at the doping profile. See, the doping profile here, N plus is maximum, it decreases in the p-type semiconductor and decreases further in the intrinsic part of the semiconductor, once again increases in the p plus region. This is N plus region, this is P region, and this is I region. The other is the I or V region, through which the generated holes must drift in moving to the P plus contact. This region is called the intrinsic region or the drift region. The P region is very thin. The space between N plus and P junction and the I and P plus junction is called a space charge region, already seen in the figure. The red diode oscillator consists of N plus PIP plus diode biased in reverse bias and mounted in a microwave cavity. The impedance of the cavity is mainly inductive and is matched to the mainly capacitive impedance of the diode to form a resonant circuit. The device can produce a negative AC resistance that in turn delivers power from the DC bias to the oscillation. So the red diode oscillator basically made up of N plus PIP plus diode biased in reverse mode and mounted in a microwave cavity. The impedance of the cavity is mainly inductive and is matched to the mainly capacitive impedance of the diode to form a resonant circuit. The device can produce a negative AC resistance that in turn delivers power from the DC bias to the oscillation. Now, how does avalanche multiplication takes place? When the reverse bias voltage is well above the breakdown voltage, the space charge region always extends from N plus P junction through the P and I regions to the IP plus junction. The fixed charges in the various regions are shown in the figure 1b. So here is the figure 1b. The fixed charges are shown here. N plus, the lattice ions are positively charged. See, the lattice ions are positively charged. In p-type semiconductor, the lattice ions are negatively charged, while in the P plus here, once again the lattice ions are negatively charged. The fixed charges shown in the region figure 1b already seen by us. A positive charge gives a rising field in moving from left to right. The maximum field which occurs at the N plus P junction is about several hundred kilovolt per centimeter. Carriers, that is the holes moving in the high field near N plus P junction, acquire energy to knock the valence electrons into the conduction band, thus producing electron-hole pairs. So what do these accelerated electrons do? They knock out the valence electrons and move them into the conduction band, thereby producing electron in the conduction band and holes in the valence band. The rate of pair production or avalanche multiplication is a sensitive non-linear function of the field. By proper doping, the field can be given a relatively sharp peak so that avalanche multiplication is confined to a very narrow region at the N plus P junction. We saw a sharp field at N plus P junction. And why is it given? So that avalanche multiplication is confined to a very small region near the junction. The electrons move into the N plus region and the holes drift through the space charge region to the P plus region with a constant velocity. From N plus to P plus region, the charge carriers are drifting with a uniform velocity. The velocity Vd is about 10 raised to power 7 centimeter per second for silicon. The field throughout the space charge region is about 5 kilovolt per centimeter. The transit time of a hole across the drift region, I region, of length L is given by tau is equal to L upon Vd, and the avalanche multiplication factor is M is equal to 1 upon 1 minus V by Vb power n, where V represents the applied voltage, Vb represents avalanche breakdown voltage, n is a numerical factor depending upon doping of P plus N or N plus P junction. N is usually 3 to 6 for silicon. The breakdown voltage for Si P plus N junction is given by rho n, mu n, epsilon s, E maximum ka square upon 2. What does rho n represent? Resistivity. What does mu n represent? Electron mobility. Epsilon s, semiconductor permittivity, and Ex is equal to maximum breakdown voltage of the electric field. Maximum breakdown of electric field. Now how does this work? How do we obtain the carrier current and the external current? To understand the working of a red diode, we consider that red diode is mounted in the microwave resonant circuit, already said by us. An AC voltage is maintained at the given frequency in the circuit. तो हम यहाँ पर एक AC वोल्टेज को मेंटेन करते हैं एक गिवन फ्रीक्वेंसी पर, and the total field across the diode is the sum of DC and AC fields. डायोड के अक्रॉस कितना फील्ड लगेगा, which is equal to sum of DC and AC fields. Initially the field is just below the critical field for avalanche breakdown. है ना, ब्रेकडाउन का जो फील्ड है उसे जस्ट थोड़ा सा कम रखते हैं. If an RF voltage is superimposed on this bias, the total field will be above the required field for avalanche breakdown during positive half cycle. तो पॉजिटिव हाफ साइकिल में जब हम RF वोल्टेज लगाते हैं तो क्या होता है, वो DC बायस जो हमने जस्ट ब्रेकडाउन वोल्टेज के नीचे रख रखा था इसके साथ ऐड होकर एकदम से avalanche breakdown की जो वोल्टेज रिक्वायर्ड है उससे ऊपर चला जाता है. The total field causes breakdown at N plus P junction and the carrier current, which is the whole current I0t, is generated at N plus P junction by avalanche multiplication, and it grows exponentially with the time while field is above critical value. जब तक फील्ड क्रिटिकल वैल्यू से ज्यादा रहता है, ये जो एवेलांच मल्टीप्लिकेशन के कारण करंट आती है वो टाइम के साथ एक्सपोनेंशियली ग्रो करती है. पर जैसे ही नेगेटिव हाफ साइकिल आएगा तो क्या होगा, टोटल फील्ड जो बायस था और जो नेगेटिव हाफ साइकिल है इन दोनों का जो सम आएगा वो क्रिटिकल वैल्यू के नीचे चला जाएगा. द टोटल फील्ड इज बिलो नाउ क्रिटिकल वैल्यू. द कैरियर करंट I0t decays exponentially to small steady state value. I0t is the current at the junction only and is in the form of a pulse. Pulse of very short duration as shown in the above figure D. Just look at this. Is a pulse of very short duration. Right? This is I0t. That is what we are talking about. The carrier current I0t reaches its maximum in the middle of the AC voltage cycle. That is 1/4 of cycle later than the voltage. In the middle of the cycle here. Right? 1/4 of cycle later than the voltage. Under the influence of electric field, the generated holes are injected into space charge region towards the negative terminal. As the injected holes traverse through the drift space, they induce a current IET in the external circuit. See, this is the current here that we are talking about, IET. So it says, under the influence of electric field, generated holes are injected into the space charge region towards the negative terminal. As the injected holes traverse the drift space, they induce a current IET in the external circuit. When the hole generated at the junction N plus P junction drift through the space charge region, they cause a reduction of electric field according to the Poisson's equation. dE by dx is equal to minus rho upon Es. Rho is the volume charge density and epsilon, as already said, as semiconductor permittivity. Since the drift velocity of the holes in the space charge region is constant, the induced current IET in the external circuit is equal to, IET is Q upon tau. And what was the value of tau? L upon Vd. So substitute here, we get Vdq upon L. Q is representing the total charge of the moving holes. Vd is the hole drift velocity and L is the length of the drift I region. The induced IET in the external circuit is equal to the average current in the space charge region. When the pulse of hole current I0t is suddenly generated at the N plus P junction, a constant current IET starts flowing in the external circuit and continues to flow during the time tau in which the holes are moving across the space charge region. So we are saying, when the pulse of the hole current I0t is suddenly generated, जब ये generate होती है ना N plus P junction पर, तो a constant current IET starts flowing in the external circuit. And कब तक flow करेगी? Continues to flow during the time tau in which the holes are moving across the space charge region. जब hole space charge region में travel करते हैं तो ये current भी establish हो जाती है. Thus on the average, the external current IET becomes, because of moving holes, is delayed by tau by 2 or pi by 2 relative to the pulsed carrier current I0t generated by at N plus P junction. तो ये जो करंट I0t है उसके रेस्पेक्ट में पाई बाई 2 या फिर tau by 2 टाइम से डिले हो जाती है. The carrier current I0t is delayed by 1/4 of a cycle or pi by 2 relative to the AC voltage. So external current IET is delayed by 180 relative to the voltage as shown in the figure D. As shown in figure D. So just see. This is figure D, right? So that is delayed by 180 degree. The cavity can be tuned to a given resonant frequency as 2 pi f is equal to pi upon tau. So f would be equal to 1 upon 2 tau, which would be equal to Vd upon 2L. Since the applied AC voltage and the external current IET are out of phase by 180, negative conductance occurs. This phase difference of 180 has produced negative conductance. So we must understand where are we obtaining the negative conductance or resistance from. And red diode is used for microwave oscillations and amplification. If we take Vd is equal to 10 raised to the power 7 centimeters per second for silicon, then the optimum operating frequency for the red diode with an I region of length of 2.5 micrometer is 20 gigahertz. So using these parameters as Vd and length of this region as 2.5, the frequency comes out to be 20 gigahertz. Now let us calculate output power and the quality factor. The external current IET approaches a square wave, which is very small during the positive half cycle of the AC voltage and almost constant during negative half cycle. तो ये जो स्क्वायर वेव बनती है जिसको एक्सटर्नल करंट IET उस फॉर्म में होती है वो बहुत छोटी होती है पॉजिटिव हाफ साइकिल में और नेगेटिव हाफ साइकिल में एक तरह से कांस्टेंट हो जाती है. द डायरेक्ट करंट ID supplied by the DC bias is the average external current. The amplitude of variation of IET is approximately equal to ID. तो जो डायरेक्ट करंट ID है जो DC बायस के कारण आती है ये एवरेज एक्सटर्नल करंट के बराबर होती है. If VA is the amplitude of the AC voltage, the AC power delivered is given by P is equal to 0.707 VA ID watt per unit area. The quality factor Q is defined as Q equals omega maximum energy stored divided by average dissipated power. The red diode supplies AC energy, hence it has negative Q, while Q of the cavity is positive. At the stable operating point, the negative Q of the diode is equal to the positive Q of the cavity circuit. If the amplitude of the AC voltage increases, the stored energy of the oscillation increases faster than the energy delivered per cycle. If the amplitude of the AC voltage increases, then what happens? The stored energy increases at a faster rate as compared to the energy delivered per cycle. So for a stable oscillation, this is the necessary condition for obtaining maximum efficiency. Now, hope we understand the basic concept of red diode. How is the negative resistance obtained? How does the avalanche multiplication takes place? I hope this video is useful for you all. Thank you very much.